Welcome back. We're diving back into the OEIS today,
Always a good time.
for sure. We're looking at A00000066.
Okay, yeah, A000066. This one's all about cage graphs.
Cage graphs.
Yeah, so imagine like the smallest graph, right, where each point connects to exactly 3 lines.
Okay, I'm picturing it.
And then the shortest loop in that graph has to be a certain length.
So, like, how many points do you need at minimal?
Exactly. That's what this sequence is all about.
Interesting. So it's like finding the most efficient way to make these, what did you call them?
Cage graphs, it's a pretty good name, I think, because they have these really restrictive properties.
Right, right. So what kind of numbers are we talking about here? What are the first few terms?
So the first few are 4, 6, 10, 14, 24, 30, 58, 70, 112, 126, and so on. You'll notice they're all even.
Oh, yeah. Is that because of Euler's handshaking lemma?
You got it. The sum of degrees has to be twice the number of edges.
Right. And since it's cubic, the total degree has to be a multiple of 3. So the number of vertices has to be even.
Exactly. You're really getting the hang of this. Now, finding these cage graphs, it's not always easy. It gets really complex as the girth, the shortest loop, increases.
So for smaller girths, it's not too bad.
Yeah, we have exact numbers for, say, girths up to 12.
Yeah.
But beyond that, things get a lot harder.
It's amazing how something that sounds simple at first can get so complicated so quickly.
It really is. And this is where the OEIS gets even cooler, because it's not just about this one sequence.
But it's all connected.
Exactly. This sequence is linked to so many others that explore related ideas, like how many cage graphs are there for a given girth?
Or maybe like cages with different degrees.
Yeah, precisely. It's like a whole network of mathematical knowledge branching out from this one concept.
It really shows how interconnected math is.
Right.
So what about those higher degrees, though? What if instead of each point connecting the 3 lines, it was 4 or 5 or even more?
That's a great question, and it definitely makes things more complex. But actually, there's something really fascinating about the minimal graph with 112 vertices and girth 11.
Okay, what is it?
Well, it turns out it's unique. Like, there's only one way to construct a cubic graph with those properties.
Wow, really? So not only is it the smallest possible, it's the only one that works.
Yep. 2 mathematicians, McKay and Mirvold, they actually proved this.
I bet that was pretty tough to prove.
Yeah, it involved a lot of computational work and some pretty serious math. And it highlights how the OEIS is always evolving as we discover new things.
It's like a living document of math. This is all super interesting, but I'm also thinking, what's the big deal? Why should someone who isn't a graph theory expert care about these cage graphs?
That's a fair point. Sometimes these things can seem really abstract, but the truth is, even something like cage graphs can have real-world applications.
Oh, really? Like what?
Well, imagine designing a communications network. You'd want to minimize connections, but also make sure there's some redundancy, so if one connection fails, the information can still get through.
Okay, I see.
And because cage graphs have that minimum number of vertices and specific girth, they can be really useful for designing these kinds of networks.
So understanding these abstract mathematical structures can actually help us build real-world things that work better.
Exactly. Sometimes the pursuit of pure knowledge can lead to unexpected but valuable applications in other fields.
It's a good reminder that even the most abstract math can have real-world implications. So we've gone from trivalent cage graphs to higher degree graphs and seen how the OEIS captures both what we know and what we're still figuring out. But I'm still curious about those graphs with different degrees.
That's where we'll pick up in part 2 of our deep dive. We'll explore what happens when we change that fundamental parameter and see what kinds of challenges and discoveries await.
I'm definitely looking forward to it.
Okay, so we've been talking about these cage graphs where every point connects to 3 lines, right? 0000066.
Right, trivalent graphs.
Exactly. But what if we change that? What if each point could connect to 4 lines or 5 or even more?
Yeah, it seems like things would get even more complicated.
Oh, they definitely do. But the OEIS has got us covered. There's actually a sequence for quadrivalent cage graphs where each point connects to 4 lines. It's A00006856.
So there's a whole separate sequence for just that 1 degree change.
Yep. And just like with A00000066, the harder part is figuring out the minimum number of points you need as the girth increases.
So even bumping up the degree by just 1 It really throws a wrench in things.
It does. It's like opening up a whole new world of possibilities and challenges, and mathematicians are still exploring all those possibilities.
I guess it makes sense. Even a small change in the rules can have a big impact on the outcome.
Absolutely. It's a great example of how even in math, you can't always predict what's going to happen just by looking at the starting point.
So we've talked about how hard it is to find these minimal graphs with higher degrees, but is there any point to all this? Like, are there any real-world applications for this kind of stuff?
It might not seem like it at first, but there are some pretty interesting applications for cage graphs, things like network design, even coding theory.
Really? Like what?
Well, think about designing a communication network, for example. You want to keep the number of connections low to save resources, but you also want some redundancy built in.
So if one connection goes down, the network can still function.
Exactly. And that's where cage graphs come in. Because they have that minimum number of vertices and that specific girth, they can give us ideas for how to build these kinds of efficient and reliable networks.
This is like these abstract mathematical objects can actually help us build better real-world systems.
That's right. Sometimes exploring these seemingly obscure areas of math can lead to unexpected and practical applications. It's all about understanding the underlying structure and how it can be applied to different problems.
That's really cool. So to recap, we started with trivalent cage graphs in A000066, then we moved on to higher degree graphs, and now we see that this whole exploration can actually have some pretty practical uses.
And that's just the tip of the iceberg, really. The OEIS is full of these kinds of connections between seemingly abstract concepts and real-world applications.
It's a reminder that math is more than just formulas and equations. It's a way of thinking about the world and finding hidden patterns in relationships.
I like that. It's about making connections and seeing how things fit together. And speaking of connections, remember how we were talking about that unique minimal graph with 112 vertices and girth 11?
Yeah, the one that's the only possible solution for those specific parameters.
Well, that leads us into some even more fascinating territory in the OEIS. There are actually a lot of sequences that point to these kinds of unique mathematical structures.
Okay, now I'm really intrigued. Tell me more.
Yeah.
All right, so we were talking about unique graphs, those with only one possible solution.
Yeah, like that minimal graph with 112 vertices and girth 11.
Right, exactly. I was wondering, are there other examples like that in the OEIS, where there's only one way to make a specific structure?
Oh, definitely. There are tons of sequences that point to unique mathematical objects, like take sequence A00000580, for example.
Okay, what's that one about?
So it lists the number of graphs you can make with a certain number of nodes where the edges don't cross.
Okay, so like a graph where the lines don't intersect.
Exactly. For smaller numbers of nodes, there are a bunch of different graphs you can make, but when you get to 8 nodes, there's only one graph that fits the rules.
Wow, so even though there are more nodes, there's only one solution.
Yep. Sometimes adding more complexity actually leads to a simpler, unique outcome.
That's pretty counterintuitive, but really cool.
It is. It just goes to show that even in math, things aren't always what you'd expect.
So it seems like the OEIS is more than just a collection of numbers. It's full of these hidden gems and unexpected connections.
Exactly. It's like a portal to a whole universe of mathematical ideas. And a lot of those ideas are beautiful, elegant, and sometimes even unique.
Well, I think that's a great note to end on. We've explored the world of cage graphs, seen how they connect to other mathematical concepts, and even discovered some surprising applications in the real world.
And we've only scratched the surface. The OEIS is a vast and ever-growing resource, and I encourage everyone to explore it for themselves.
Yeah, don't just look at the numbers. Think about the stories they tell, the puzzles they represent, and the connections they reveal. It's a whole world of mathematical wonder waiting to be discovered.
Well said. Thanks for joining us on this deep dive into the OEIS. Until next time, keep exploring.
See you then.